So I've given you a picture of the history of our understanding of gravity, especially through what is arguably the most successful theory of all time, which is Newton's theory of gravity. And now, in the way science develops, it doesn't mean that Newton was wrong. It means that we find reasons why our theoretical understanding of a subject has to evolve. And in this case, we're getting to the point where we saw, for the first time, I showed you one feature where, at least naively, we found the first place in nature where Newton's theory of gravity didn't quite get the right answer. 10% off for the orbit of Mercury around the sun. There are other areas where Newton's theory didn't really help very much or be able to address it. It turns out that the Earth's field, it has variations. There's no real way, if you think of it as just simple mass, to understand where the variations come from. But more importantly, conceptually, there were some missing pieces in Newton's theory, and he even understood part of that. The first one is the most important, maybe, and that is that Newton did not address at all what caused gravity. He took the fact that objects that have mass attract each other and made a theory to describe that, but he didn't tell us what caused gravity. Interestingly, and I don't have time, if you look at what people did with that between 1687, when Newton basically brought his theory forward, and the 20th century, mostly the attempted explanations were electromagnetic in origin, which clearly has nothing to do with what really caused gravity. So people recognized that what caused gravity wasn't explained, but no one gave a good explanation of what caused gravity. So that was an unanswered question at the time of Newton and after Newton. And as I say, almost anything you can find where somebody tried to explain it, they did it usually with some sort of electromagnetic explanation. For Newton, gravity was simply just a property of objects that have mass. But he couldn't explain how gravity was able to span somehow between these two objects that didn't touch each other. And this bothered Newton, and he wrote about it. Yeah, he didn't like the idea of, and he used the word action at a distance. Later, I'll talk about even harder problem, which is instantaneous action at a distance in just a minute. But he actually wrote that he was troubled by action at a distance. I'll give you his quote in a minute. So the conceptual problem of the apple falling out of the tree, the conceptual thing that we have, and why it falls, is something that Newton didn't describe. So that's the way we think of a theory as being incomplete. It didn't describe something. And we'll see that in Einstein's case, he does describe why. So that already is a step beyond a theory that already existed. It's very dramatic in this case because we have a theory that was so successful for so long and with almost nothing except possibly the orbit of Mercury that gave any hint that it was not valid, yet it wasn't able to do some very important things. For example, to explain why the apple falls from the tree. This is where I do Newton's words. Newton proposed then that gravity must act first instantaneously, regardless of the distance, or else he couldn't conserve angular momentum. So he recognized that it has to happen instantly. Instantaneous action at a distance. This is a very difficult concept, and he called it actio in distans. Action at a distance, there's no mechanism proposed in gravity to transmit gravity. And this is his words. He says that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed with one another is to me so great an absurdity that I believe no man who has in philosophical matters a completely competent faculty of thinking could ever fall into it. So he basically found this to be a complete puzzle. As I'll show, it gets answered by Einstein's theory. This is the equivalent formula in Einstein's theory to Newton's formula. For this course, we're not going to go into that. I'm going to pick out just enough of it to be able to talk about gravitational waves in the next lecture. But basically, what is done schematically that we can come away with is that what Einstein does is unify space and time. And it's that unification that creates a geometric theory that is Einstein's conception of gravity. In some sense, it unifies space and time. So in 1915, this is 10 years after Einstein had introduced the special theory of relativity, which we're all familiar with, E equals mc squared, and solved several other very important problems in physics in a period of a few months. He then spent a decade developing his theory of general relativity, which is basically adding acceleration to the theory of special relativity, and it then becomes a theory of gravity. So in Einstein's case, gravity is not a force. So the first thing we did is write down a force for the picture that Newton had, but in this case, it's not a force. Instead, it's built into the structure of space and time. Space and time, in this case, are curved, and nothing can avoid feeling any curvature that exists in space and time. And that's what makes gravity universal in Einstein's case. So it's a completely different concept than we're used to. The special theory of relativity of an observer at rest or in uniform motion observes the same laws of physics, including the same speed of light. In general relativity, it also applies to observers falling freely in a gravitational field that they see the same thing. This is an important concept. I'll show you the evidence in a minute qualitatively. This is called the principle of equivalence. The key point is that all objects experience the same acceleration in a gravitational field, and it doesn't matter what the circumstances are. In a kind of empirical way, that's observed, for example, by astronauts that are on the space station. Astronauts that are on the space station are at an altitude of 400 kilometers. The radius of the Earth is 6,370 kilometers. The force of gravity, the gravitational strength at the International Space Station is only 88% of the surface, and therefore they experience various effects, but consistent with the same physical laws. There's been at least one airplane journey to try to test the principle of equivalence qualitatively by making it go up and down, where it experiences 0G up to 2G, and during that time, people's experience has been recorded. And so, as far as we know, the principle of equivalence is good qualitatively. It's a little more subtle. When we look at the consequence, we have basically an inertial frame of reference, or we have to translate ourselves into the frame of reference of whatever's falling, free fall. And as we do that, we see that something that goes straight, if you're in free fall, has to curve. And this basically is that light itself must bend if it's in a gravitational field that we experience. That also means that if we have an observer and we're moving away from a source, we see the wavelength shift, and we see what's called redshifted light. If we move toward it, the light must be blue shifted. So these are consequences, basically, of the theory. The pictorial picture is the one I'm showing here. This is, unfortunately, all we can do in a picture like this is show you a two-dimensional or three-dimensional graph. And I have to emphasize that in Einstein's theory, it's four-dimensional, three space and one time. So every intersection that you look at on this picture has no distortion. If you look out here, they're fine, but if you look near a mass, each of these points got distorted in space, which we see here, but also each of these points is distorted in time. So it's space and time together. I just can't show you that pictorially. So if I have the Earth here, then it basically distorts the space-time around it. If I then have an apple that's above the Earth, it obviously falls toward the place that's the Earth. So in Einstein's theory, the warpage of space-time basically gives you a picture that you can see here. Of course, it's much more detailed mathematically than it would fall. Also, the moon going around the Earth has a centripetal force pushing it out, but the gravitational force due to this that pulls it in, and so you can describe the orbit. So it's hard to do this pictorially, but crudely, that's the picture that we have when we have Einstein's theory of gravity. Instead of having a force between two things, we have a distortion of the space that the objects go through. I mentioned earlier that we had a problem in Newton's theory, which he recognized. There were two problems, really. One is what causes the force. The second one is one that he recognized, and that is action at a distance. In fact, instantaneous action at a distance. And probably the easiest way to think about that is if the sun were to disappear right now, we wouldn't know it for 8 minutes, which is the time it takes for light or electromagnetic radiation to come from the sun to us. And if we had instantaneous action at a distance, we know about gravity immediately, which is not physically possible. And so it also takes 8 minutes for the gravitational signal to get here, because in Einstein's theory, the speed of gravity, or gravitational waves, which we'll see, is the same as the speed of light. Since we knew about light first, we call it the speed of light. It's the same speed, and it's finite. It's very fast, but it's finite. And so the 8 minutes is also how long it takes for a gravitational signal to come. So there are two very important conceptual problems that are solved by Einstein's theory. One, instantaneous action at a distance, which you don't have in Einstein's equation. This matters more and more when we start talking about astronomical questions, when we talk about distance objects that are in the distant universe. When we talk about gravitational waves, you'll see some of that. And in fact, in case I forget, somebody can remind me, we know now to empirically, to basically 1 part in 10 to the 15, that gravitational waves travel at the same, or gravity travels at the same speed as the speed of light. And it comes about from the fact that we see a signal from merger of two neutron stars 100 million light years away that are within 1.7 seconds of when an electromagnetic signal was seen. And 1.7 seconds out of 100 million light years is a part in 10 to the 15. So we know that the speeds are the same as Einstein said, to 1 part in 10 to the 15. So that's the second question. For a theory, so fixing the problem of mercury, which I didn't do yet, I'll show you the data. But Einstein's theory fixes the one empirical problem that existed, that was mercury. It also solved these two conceptual problems, instantaneous action at a distance being one, and why the apple falls being the second. But any new theory in physics, certainly one that's going to replace the most successful theory ever that was more than 200 years old, has to make new predictions. And the new prediction that was made and is so well known from Einstein's theory is that it made the prediction that not just massive objects, if they're in this curved space and time, will be affected, but also massless objects, or light itself. So light itself, if it goes near a massive object, will be bent in Einstein's theory. And that new prediction that he made was also quantitative. He could calculate how much it would be bent. And he did that. So basically, he predicted this in 1915 in the original theory of general relativity, that light would be bent. And he predicted how to test it. And the way to test it was to look at a full eclipse of the sun. At the same time, while you're looking at it, stars that are behind the sun move toward the sun or behind the sun. And you can see the signal, you can see the light coming from it apparently bend as it goes behind the sun, in a picture that's a little bit like the one that I've drawn here. So he proposes in 1915. He then motivated an expedition that went east toward what was new at that point, the developing Soviet Union. And the astronomers that went had a lot of equipment to try to measure an eclipse of the sun that I think was 1917 about. And they got arrested. There was a lot of confusion. It was the time of the Soviet revolution. And Einstein and others had to do a lot of work to get him out of jail, and nothing was measured in terms of an experiment. Instead, it reverted to the second eclipse of the sun that could be done after Einstein's theory came, and that was in 1919. And the eclipse of the sun could be observed from the southern hemisphere of our planet. And the problem of trying to see that was picked up by a British physicist, Sir Arthur Eddington, who became Sir Arthur Eddington as a result of the measurement, I guess. And he took on the problem of measuring the bending of light from a picture like this, the eclipse of the sun in 1919. So in 1919, the idea, which you can kind of see here, is that if you pick exactly the time that the sun eclipses, it takes a couple minutes while it's eclipsed, and you watch stars behind come, you can see whether the parent beam coming to you has bent. And that was what he took on to do. And the stars behind it, in this case, were a cluster of stars called the Hyades cluster. And so the picture shown here is that the observed position during the eclipse is here, while the real position is here, just because the light is bent. It looks like it's in a different place than it actually is, and he made those measurements. Just another picture of what's happening, the light bending from behind the sun. And during the solar eclipse then, he measured it. He did it by having two different observations. Because of time, I'm going a little bit fast here, but it's in my notes. He had two different places that he put, that he did the measurement, one in an island off of Africa, one in South America. And they both gave consistent pictures of gravitational waves. This is just some of his data, which I don't have time to show. By today's standards, This wouldn't have been accepted as a discovery of bending of light. We have rather rigid criteria somehow that have developed because of false results. That statistically, something has to have almost no probability of being wrong. And of course, you couldn't do that with a small amount of data collected in 1919. Nevertheless, he was right. And so the eclipse crossed the southern hemisphere, shown here, Africa and South America. You have two stations where he measured it, one in South America, one on an island off of Africa. And the data altogether, there was a bunch of plates, data, and basically he declared that light bent. This, of course, caused a lot of sensation. This is the article from the New York Times right after the claim of the bending of light. And you can see it's rather dramatic. Lights all askew in the heavens, men of science, more or less agog over results of an eclipse observation. Stars not where they seem to be, were calculated to be, where they're calculated to be, but nobody worries, and so forth and so on. So that's not clear the journalists understood very well. But they reported the result. It's actually this result and the publicity it got that made Einstein a household name in the world. He became known everywhere in the world, was famous from that point on. For a physicist, for us, he was famous as of what he did in 1905. And there was a big celebration in the physics community worldwide for what he did on the 100th anniversary of 1905. But in terms of the world community, it was this discovery of the bending of light that made him so well known in the world. So this result, as I say, statistically, if I go back and look at it now, we would believe it. It's not 5 sigma, whatever terms we use. There was a very good experiment that followed in 1922 at the Lick Observatory, and it had much better statistics. It measured better than 1% the bending of the light. And so this became true, and of course, it's been done many times since then. And in the same way, the fractional redshift that we calculate is right, and so forth. So this whole problem with the bending of the light, the redshift, all of that has been done very well, and none of this would have been there out of Newton's theory. So, and there's various astronomical effects, the masses of white dwarfs and so forth that are found and determined only because you have these effects from Einstein's equations. So it's become a tool of astronomy, measuring the redshift, measuring the effects themselves. In modern case, in terms of trying to not do astronomy, which, as I said, we see it being used now as a tool, that there's also many tests that have been done and will be done to test general relativity itself, just like Einstein's theory. Is Einstein's theory of general relativity the right theory, or do we have to modify it and look into the future? And of course, in a limited range, where I've shown you some results, it solves the problems that Newton's theory couldn't. But as physics develops, we're not sure that if we look, for example, in the region where gravity is very, very strong, whether it is the right theory or possibly some alternatives are better. And that's the way science evolves. For the purpose of these talks and the continuation today, I'm going to use the Einstein's equations, Einstein's prediction of gravitational waves to go into gravitational waves. But as a theory itself, we still have a theory of gravity that deserves to be tested and is being tested. There's alternate theories that we have to understand what the right theory of gravity is. Due to time, I don't have the time to go through several of the tests, but let me mention them. We lost some time earlier. But let me mention a little bit some of the tests that have been done. First, the test of the equivalence principle. I showed you basically qualitatively a plane going up and down, and as you see people experiencing the same laws, whether they're in no gravity or little gravity. But there's experiments also trying to measure whether the equivalence principle works and put limits on it. And we've seen that no differences in acceleration have been found. For example, to 1 part in 10 to the 15th tests of equivalence principles. There's tests of the inverse square law that have been done very, very accurately. So this is the kind of way we try to push physics to see where the present laws work and where they may not, and where we may have to alter, we may have to alter the theory beyond where we are. And that's true of Einstein's theory as it was for Newton's theory. We have some effects that have become very practical using this whole theoretical concept, and that is because of the bending of light, we have a whole lensing question, and this has become kind of a cottage industry for cosmology, studying cosmology and astrophysics. I'll mention a little bit of this as I get to the last lectures, when I'll talk about the Hubble constant and so forth. But let me just mention a few here. The gravitational lensing, which is using Einstein's equations, has a side effect of being tremendously valuable for measuring the mass distribution of galaxies, galaxy clusters, determining the rate at which the universe is expanding, what we call the Hubble constant, which I'm going to come to and talk about in detail in a couple lectures. Constructing the mass maps of the universe itself, where the masses are. Understanding structures like what's called the galactic bulge, looking for dark objects in the galactic halo, detecting extrasolar planets. These are all things that are done. My main point is that you learn more physics, in this case, the effects of general relativity, and you're able to use it in a different way to become a very important tool in doing another science, in this case, astronomy. And so my message basically is how important the theory is in terms of not just what it is trying to solve in terms of gravity, but in what it enables you to do otherwise. There's many more detailed experiments to do, and some that have been done, testing some of the details of Einstein's theory, testing the space curvature, or what we call frame dragging, where when the frame of reference doesn't quite come the same. Again, I don't have time to show it in detail, but there's been a detailed experiment in space to do this. There's been tests of what's called the geodetic precession and frame dragging to pretty good accuracy these days, which are some of the basic effects of the space-time effect. The ideal test of general relativity is an accurate clock in a very strong gravitational field. This provides, the closest we have is provided by pulsars in a close binary system of compact objects. The first one that was found I'm going to talk about because it's important for gravitational waves next lecture, which is called the Hulse-Taylor pulsar, and looking at the evolution of the period of that pulsar. It was very important in establishing that gravitational waves exist, which I'll talk about. But there are other examples, and there will be more in the future. There's a double pulsar, a double neutron star system in which both neutrons are pulsars that can be used to do some tests of general relativity. So on one hand, we test general relativity and try to understand how accurate it is or where we might be motivated to have alternatives. On the other hand, we also are looking at outcomes of general relativity. The most clear and obvious one is what we call gravitational lensing. That's shown in this picture here. And that is that we have an object in space, and there's light coming from behind it. It gets focused, and we see that. And it can even be seen rather well with a small telescope. It's a picture behind a dark object. Or the most famous one is what's called the Einstein cross, which happens to be 4 images that are seen from an object, generally in the southern hemisphere. I want to make one other general comment about general relativity before I go on to gravitational waves, and that is this whole concept of curvature of space-time, the differences from Einstein's, from Newton's equations and so forth, may seem very abstract. And so I want to bring one everyday feature to you, and that is that all of you use general relativity every day if you use this thing, probably. And that is the GPS system. So it turns out that the GPS system uses general relativity, and if it didn't, you wouldn't get the right answer for guiding yourself around. So this is the reason why. The GPS system is the original one is 24 satellites around the Earth. Each of the satellites is going at about 14,000 kilometers an hour. And one of the expressions we learn when we learn relativity is that moving clocks tick more slowly. It's what happens when you go fast. And that's special relativity, not general relativity. So the fact that the satellites are going 14,000 kilometers an hour, which is a finite fraction of the speed of light, you have to make a correction in the satellites. So what happens is you measure the time it takes the signal to go back and forth between you and whatever satellites are in your field of view, up to maybe 6. And that correction for special relativity, made in the electronics, in the satellites, is 7 microseconds a day. Well, we all know how special relativity works. We have many examples of it, and it existed before. General relativity, which is I'm talking about today, also is required to get the right answer for GPS. General relativity is needed because the satellites are far enough above the Earth so that the gravitational field from the Earth felt at the satellites is about 1/4 what it is on the Earth itself. And if I then take general relativity, I have to make a correction. In fact, this correction is the other sign. Clocks go faster, and the correction is 45 microseconds a day. So the total correction that has to be made in GPS is 38 microseconds per day. When GPS was created, it was created by the US military. And it was a very was not a difficult problem by the advisors to the military that they had to make a correction for special relativity. But it took a lot of studies and convincing before the military became convinced that they had to make a correction for general relativity, which they did. And so this correction is made. I can go through for you the numbers, but the accuracy required if I want to stay on a road, say 10 meters wide, that's a pretty wide road, using GPS, is about 30 nanosecond accuracy. If I take 38 microseconds per day, that means that if I didn't make the correction, I would only stay in my 10-meter road for about 2 minutes. So you need these corrections. They're not just academic to make GPS work at the level we use it every day. So general relativity matters, even in everyday life. We're, of course, going to talk about it in a different way. Where it's most interesting to physicists is not for GPS, but in the limit where gravitational fields are extremely strong. And the two places where that's the most true, where we actually, not just mathematically have to grapple with it, but physically have to understand it, is the early universe, where the fields were very, very strong, and in regions near black holes, the horizon of black holes. So these in a sense, are the two places where physically we can bring together possible observations with understanding general relativity better than we do today, whether it's Einstein's or variations of Einstein's theory of general relativity. This is where general relativity itself becomes, in technical terms, nonlinear, and for us as physicists, interesting. We aren't very close to any black holes to test it, unfortunately, and we can't see light and other electromagnetic radiation from black holes, so it'll be a while before we can do these tests directly in black holes, but we're becoming closer. We've seen pictures I showed you from the Event Horizon Telescope of black holes. We're now able to measure various properties of black holes with gravitational waves, and so one could hope that we can pursue some of this science of strong field gravity from black holes in the future. Also, gravitational waves are not absorbed in the early universe, and so in the future, again, they represent a way to get to the early universe, a way to also understand general relativity in the strong field of the early universe, when we can detect gravitational radiation or wave radiation coming from the early universe. Neither of those are we able to do experimentally now, but in the future. So, in 1916, 1 year after Einstein gave general relativity, he predicted that there was gravitational radiation, gravitational waves. And that first publication is very small. It's a few pages. I showed it here. It's not a very good paper. It's basically it doesn't derive gravitational waves from first principles of what he had introduced a year earlier, general relativity. Rather, what he does is by setting up the equations of general relativity in a particular way. I'll do something similar next time. He shows that they have pretty much the same form that we're used to from electromagnetism, and we know in electromagnetism we have electromagnetic waves. So Einstein in this paper basically, by analogy and by being Einstein, makes the leap that if the equations look like the equations of electricity and magnetism, then there must be gravitational waves as well as electromagnetic waves. That paper has a serious factor of 2 error, which would have been bad for us in trying to measure gravitational waves later. He fixes all that in a paper 2 years later. So he wrote a second paper in 1918, and he corrected the errors in the first paper. He never admitted there were errors, he just fixed them. And more importantly, in the second paper, he actually talks about the source of gravitational waves, how you make gravitational waves. And if you remember, when you talk about electromagnetic waves, they were discovered by a physicist named Hertz in the 1880s by taking in a charge, 2 charges, a plus charge and a minus charge, and oscillating them, going in the next room and seeing that it created electromagnetic waves, took his detector and moved it forward and backward, and saw that it was wave-like. In this case, the source of gravitational waves, Einstein tells us in his 1918 paper, are not a dipole like his 2 poles, but 4 poles, a quadrupole. And we use that to find sources of gravitational waves. If I have 2 objects going around each other like this, that creates a so-called quadrupole field, and that's why we looked for sources like this. So gravity needs to obey the principles of relativity. That is, no signals go faster than the speed of light. But if they did, it would violate relativity. Gravity basically then changes or ripples out an accelerating object into what's called gravitational waves. I'll talk about it next time, but the waves themselves are ripples in space itself. There's no analogy in the classical theory of Einstein of anything like a graviton to a photon. There's no object with it, just a wave that goes through space itself and distorts space and time. And we'll talk about that next time. We'll talk about how you make the waves from an object like this, and then what's involved in detecting them. I have a little bit more to talk about why people didn't accept the ideas of Einstein right away in 1916 and 18. And it took another 40 years before it was accepted that gravitational waves exist and should be able to be detected. That was about 1960. I'll give you that little bit of why that was a problem and talk about the detection next time. Thanks.